mentioned this word before, the discriminant, when we were talking about finding the y value of the vertex. You might remember that was minus the discriminant on 4a. It has a lot more uses. So a reminder, discriminant, b squared minus 4ac, that bit under the square root sign in the quadratic equation. Okay. Some of the things we can use it for. Okay, we've seen the idea it can find us the maximum or the minimum. Okay. It can also tell us whether a root is rational or irrational, because remember, it's the bit under the square root sign. So if it's a perfect square, then I know it's going to be a rational number, because I can find the square root of it. If it's not a perfect square, then it'll be irrational. Other things, if the discriminant is greater than 0, then we know, well, the picture will have two x-intercepts, so it cuts the x's twice. But what we say is we have two different real roots. So there's two solutions, basically. Discriminant is equal to 0. It touches the x-axis once. Now here's the subtle difference, I guess, between solutions and roots. They are the same thing. But when we have an equation like, let's pick a simple one. X squared equals 0. We say there's one solution, x equals 0. But there are actually two roots. It's just that they're the same. Right? So when it comes to talking about roots, if the discriminant is equal to 0, they will be the same, but there are two of them. One answer, but two roots. And if it's less than 0, then there's no real roots at all. So it'll never touch the x-axis. There are still two roots, by the way, but they're now what we call two imaginary roots. But we don't have to worry about that in this course. So we simply say, well, there's no real ones. This is what I was just saying before. If the discriminant turns out to be a perfect square, then I know the roots are rational. Otherwise, they'd be irrational. So, okay, we're going to describe the roots of this particular quadratic. We're going to find the discriminant. In this case, it's minus 83. And so really, there's only one thing I know, and that's, well, there's no real roots. Bit hard to classify them when they don't exist. So that's the best we can do with that one. Let's have a look at another one. In this one, we do get a positive number. It's 60. So there's lots of different things I can tell by the number 60. It's greater than 0. So it tells me there's two solutions. I know they're real because they exist. I know they're irrational because 60 is not a perfect square. So to write all of that down, I can say there's two different, real, irrational roots. All with one number. Who would have thought? So this time we've got to work out the value of k to make this have equal roots. So we've got to ask ourselves, well, what's the condition that makes a quadratic have equal roots? And the condition is, well, equal roots will occur when discriminant equals 0. So I'm going to solve that. B squared minus 4ac is equal to 0. I end up with k is 9. Another way, I guess, of looking at this, if you didn't want to use the discriminant idea, is it would need to be a perfect square. So k would have to be half the coefficient of x, all squared, so you could make it a perfect square. And half of 6x is 3x, square the 3, you get 9. So another way you could do that question. To have unreal roots. Well, unreal was when discriminant was less than 0. So in this case, we need to solve discriminant less than 0. B squared minus 4ac. Solving that one, we get k is greater than 2. K is greater than 2. To have real roots. The condition for real roots is greater than or equal to. Because we haven't said anything here about them being different or being the same. We've just said real. So one condition was if it's greater than 0, we'd have two different real roots. If it was equal to 0, we'd have two equal real roots. Combine the two conditions together, it's going to be greater than or equal to 0. That's the inequality we will solve. So b squared minus 4ac, we get k squared is less than or equal to a quarter, so k would be in between minus a half and a half. Then you might be looking at this thinking, well, hang on, how did this slip into a question about the discriminant? For what value of A is the line y equals ax a tangent to this particular circle? Well, if I said to you, I want to find where this line, y equals ax, cuts this circle, how would you find out? Yeah, you'd solve it simultaneously. Well, I don't really want to find the answers, because all I want to know is it's a tangent. So if it is a tangent, how many solutions should I get to that equation? Just the one. And so I can use the discriminant. So we're going to do the first instinct where I'm going to substitute in y equals ax. So I've got my a squared x squared there. Let's make it look like a quadratic equation. So I'll group the x squareds, group the x's together. I'll say, well, look, I don't want to solve this equation. I don't need to solve this equation. All I need to do is find when the discriminant is equal to 0. So this idea of something being a tangent, when two curves meet, them being tangents, comes up a lot. We don't actually solve the equation, we just want to know when it has one solution. So b squared minus 4ac, and whoa, actually 100 goes into everything there. 3a squared plus 4a. We get two possibilities, a equals 0 or a equals minus 4 on 3. It would be a tangent. Ta-da! 8. F we shall now go have a look at.